Hello students, in this video we are going to discuss 6.11, 6.12, 6.13 and 6.14 from System of Particles and Rotational Motion of class 11. Those till now who didn't subscribe, kindly subscribe the channel. Coming to the solutions, 6.11. A solid cylinder of mass 20 kg rotates about its axis with angular speed 100 radian per second. So this is a solid cylinder, assume, and it is rotating about its axis with angular velocity 100 radian per second. The radius of the cylinder is 0.25 meter. The radius is 0.25 meter. So what is the kinetic energy associated with the rotation of the cylinder? We need to find out rotational kinetic energy. What is the magnitude of the angular momentum of the cylinder about its axis? So angular momentum also we need to find out. So the given values are: mass of the cylinder is 20 kg. It is rotating with the angular speed 100 radian per second. Its radius is 0.25 meter. All are in terms of SI system. So therefore, rotational kinetic energy we need to find out. Here, rotational kinetic energy is half I omega square, but I we don't know, we have to calculate. And angular momentum we need to find out. To get these two, first of all we have to find out I also. Coming to I, moment of inertia is equal to half mr square if it is solid cylinder about its axis. That is equal to half, mass is 20 and its radius is 0.25 whole square. So if you simplify, you will get this value 0.625. The SI unit of moment of inertia is kilogram meter square. Mass is in terms of kilogram, r square is in terms of meter square. Now while coming to the rotational kinetic energy is nothing but half I omega square. It is look like half mv square type. So that is equal to half I value already we calculated 0.625 into omega square, that is 100 square. So after simplification we will get 3125 joule. And angular momentum with respect to that axis is equal to I omega, that is 0.625, omega value is 100, that is 62.25. The units of L is kilogram meter square per second. So these are the values of L, Ke and I. Coming to 6.12. A child stands at the center of a turntable with his two arms outstretched. The turntable is set to rotating with an angular speed 40 revolutions per minute. How much is the angular speed of the child if he folds his hands back and thereby reduces its moment of inertia to 2 by 5 times of the initial value? Assume that the turntable rotates without friction. Here, whenever on a table there is a child initially stretching his hands like this, first case, second case, this child is folding hands like this, then automatically the angular speed increases as per conservation of angular momentum. momentum if there is no external torque is acting. Initially angular momentum is Li, finally angular momentum is Lf. Both values will be equal. So the given values, initial angular velocity omega I is equal to 40 revolutions per minute, and the final moment of inertia is equal to 2 by 5 times of initial angular momentum. Initial moment of inertia. So, from the conservation of angular momentum, we can write initial angular momentum is equal to final angular momentum. Initial angular momentum is nothing but actually I omega I is equal to IF omega F. From this, we need to find out the final angular speed. So the final angular speed is equal to I omega I divided by IF. So I omega I is nothing but 40 divided by IF is nothing but 2 by 5 times of I will be get cancelled, and this value will be 100. Units are in terms of revolutions per minute only. So this is the angular speed. Angular speed increased from 40 to 100 whenever the child folds his hands as shown. Coming to show that the child's new kinetic energy of the rotation is more than initial kinetic energy of the rotation. So omega F is increased, therefore automatically it will increase. Okay, we'll show mathematically. So this is for A, this is for suppose say B. So the initial kinetic energy, so kinetic energy rotational initial, so that is equal to half I omega I square, that is equal to half I into 40 square, that is nothing but 800 I. Now kinetic energy rotational final value, half I final omega final square, that is half I final is equal to 2 by 5 times of I initial into omega final value is nothing but 100, so whole square. So that is equal to 2000 I initial, we will get it. So from here we can show that kinetic energy final value is more than kinetic energy initial value. Otherwise, we can write kinetic energy rotational final divided by kinetic energy rotational initial is equal to 2000 I divided by 800 I. Its value is nothing but 2.5. So that means we can write kinetic energy rotational final is equal to 2.5 times of kinetic energy rotational initial. So like this also we can show. And how do you account for this increase in kinetic energy? Actually, from first case to second case, the kinetic energy is increased. From where the child got this kinetic energy? Which type of energy is converted into kinetic energy? So here, while he is folding, so the reason is due to the internal energy of the child, which he uses in folding his hands. That means the internal energy is converted into kinetic energy. So how the internal energy is given while he is folding his hands? So that means whatever the internal energy is there, that is converted into kinetic energy. That means here it is not violated the law of conservation of energy. It is obeyed conservation of energy only. That is internal energy is converted into kinetic. That's why there is a decrease in internal energy and there is increase in kinetic energy. Coming to 6.13. A rope of negligible mass is wound round a hollow cylinder of mass 3 kg and radius 40 cm. What is the angular acceleration of the cylinder if the rope is pulled with a force of 30 Newton? What is the linear acceleration of the rope? Assume that there is no slipping. Here the given data is, so mass of the cylinder is given as 3 kg and its radius is 40 centimeter, that is 40 into 10 power minus 2 meter, and force applied is 30 Newton. Now we need to find out angular acceleration. So the angular acceleration alpha is equal to tau divided by moment of inertia. But tau we can write in terms of force and the radius of the cylinder divided by moment of inertia for hollow cylinder is mr square. One r will be get cancelled. F divided by mr, that is 30 divided by, and mass we can use capital M or small m. M is nothing but 3, r value, okay, here also we can take capital R, that is 40 into 10 power minus 2. So after simplification we will get alpha is 25 radian per second square. And one more thing, linear acceleration. So the linear acceleration A is equal to r alpha, radius into angular acceleration. That is 40 into 10 power minus 2 into 25. That is equal to, we will get 10 meter per second square. So this is linear acceleration of the rope. Coming to 6.14. To maintain a rotor at a uniform angular speed of 200 radian per second. Uniform angular speed, that means angular acceleration is 0, torque is 0, net torque. An engine needs to transmit a torque of 180 Newton per meter. That means to maintain uniform angular speed, the torque acting on this one to overcome the friction actually. What is the power required by the engine? Uniform angular velocity in the absence of friction implies zero torque. If friction is not there, this torque is not needed. But practically some friction will be there. That's why to overcome the friction, this torque is needed. In practice, applied torque is needed to counter frictional torque. Assume that the engine is 100% efficient. Now, well, coming to this given data, we have angular speed omega is equal to 200 radian per second and torque is equal to 180 Newton meter. Now we need to calculate the power. Power P is equal to tau into omega. That is equal to 180 into 200. That is equal to 36,000 in terms of SI system watt. That is 36 kilowatt. So this is the power required by the engine. So these are the solutions in this one. Thank you. Those who didn't subscribe, kindly subscribe the channel.